In this session, we will continue talking about the genetic algorithm. So, I had just introduced the algorithm for the genetic algorithm. So, we will continue by seeing what are all the operators that we are talking about here. What is selection, what is crossover, what is mutation. So, the basic algorithm which we studied, which is called the simple GA or the SGA, all the strings are actually binary like we were talking about here. So, they are all binary, either zeros or ones. All the elements in the string are either 0 or 1. So, let us now come to selection. So, what do you mean by selection? So, we have a population of strings. So, suppose you have n strings in a population, we need to generate the next population of strings. And to generate the first population, next population, we need to first carry out selection. So, we select some of the strings from this population. So, the idea is that the strings with better fitness are chosen to go into the next generation. So, the strings with higher fitness have a larger probability of being chosen in the next generation, and those with very low fitness may just get weeded out. Okay. So, for example, if we have strings like this, okay, so we have 4 strings here and we can see this represents string 6, and if your fitness is like x squared, you will get 36 here. This is 12, so you get 144. This is 9, so you will get 81, and this is 3, so you get a fitness of 9 for this. So, suppose you add up all these, you will get 270, and if we divide each of these by 270 and say multiply by 100, it tells you what is the percentage of the total of each of these strings. So, the first string is say 13.3% of the total, okay. The second one is 53.3%, third one is 30%, fourth one is 3.3%. So, here it is represented over here. So, we can see that this is your string 2, this red one, and this yellow one gives you your string 3, and this blue one will give you your first string, and the green one is your fourth string. So, you can look at this like something like a roulette wheel which is used when you gamble, right. So, you have a roulette wheel which you turn, okay, and then it depends on where it stops, etc., right. So, suppose we have a roulette wheel and you are going to turn the roulette wheel, and wherever it stops, okay, so that string is going to be chosen to go into the next generation. Obviously, we can see that because if you look at the circumference of this circle, you find most of it is occupied by this red string, and next the yellow, the orange string. So, what happens is that there is a higher probability of this string being chosen to go into the next generation, and there is a little lower probability of this string and little lower of this, etc. So, this is actually a stochastic method of finding the string which goes into the next generation. Here the same thing is shown again. So, the chances are proportional to the fitness. So, the roulette wheel is, can look at it like a circular thing. So, if we have say only 3 fitness, 3, 1 and 2, this one string A will occupy half the circumference, and string B will occupy 1/3 of the circumference, and 1/6 of the circumference, and C will 1/3. Okay, so same like you have a fitness, you have a roulette wheel which you are going to turn basically. So, there are a number of selection schemes that we can talk of here. One is what is called the deterministic sampling. The second one is remainder stochastic sampling without replacement. Third one is stochastic sampling without replacement. Remainder stochastic sampling with replacement, stochastic sampling with replacement, and stochastic tournament. So let us see what all these actually are. So stochastic sampling with replacement is the same as the roulette wheel selection. So we have that as one of them here, stochastic sampling with replacement, right. So that's the same. In other words, once a string is chosen to be put into the next generation, you are going to replace that string back into the set of strings which you are going to work with. If you don't replace it back fully, then it's called stochastic sampling without replacement. So how would you do this? Suppose the string had a particular fitness, you can reduce its fitness by 0.5 or something like that, which makes it less likely to be chosen than, once it is chosen, for it to be chosen again, there is a probability which is the probability is reduced. And when you say remainder stochastic sampling, it means the first part of the selection is done deterministically and then the last part is done stochastically. We will see what we mean by that. Okay. So how is the deterministic sampling done? You take your fitness of string I and divide it by the overall total fitness of all the strings together. Okay, so you will get a value between 0 and 1 and you multiply that by n. If you have n strings, okay, you have n strings in your population, you multiply it by n and you look at the integer part of that. So the integer part may have say 1 or it may have 2 or 3. So whatever number of samples the integer part says, you put so many samples into the next generation. And then what you do is you take only the fractional part and you sort those out. And after sorting those out, you from the top, whichever string that represents, those strings you put into the next generation. So that is what is called the deterministic sampling. Now in some cases what they do is that deterministic sampling is done for the integer part and the fractional part is taken and you do stochastic sampling over there. So that's why you get all these different types of sampling here. Stochastic sampling with replacement. Each time a string is selected for mating and crossover, its fitness value is decreased by 0.5. Okay, and whenever it falls below 0, the string f will no longer be available for selection. And remainder stochastic sampling, like I said, the strings are selected according to integer part in a deterministic manner and the fractional part are used and it's done in a stochastic manner with the roulette wheel. And what is stochastic tournament? Two strings are drawn independently using roulette wheel selection. And then you see which string has the higher fitness and that is the winner and it is inserted into the next generation. So we can see that there are a number of different ways in which the selection can actually be done. Okay, then we come to crossover. What do you mean by crossover? So you take two strings. So out of all the population, you have to take two strings and you have to choose one crossover point. For example, if these are the two strings, you have decided to have a crossover point here after 3 elements. Okay. So once you get the crossover point, all the elements which come after the crossover point are interchanged. Okay. They are swapped. So these two are brought here and these two go up and you get these as the new strings. So on the right of the crossover point, you interchange the elements of the two strings. So that's what you mean is the basic, this is known as the single point crossover. So there are many variations of the crossover also. So this is the one point crossover where we are talking about. So you are choosing one crossover point like this and all the elements after that they are interchanged basically. and you also use what is called the probability of crossover. So, probability of crossover is usually taken between 0.6 and 0.9. It's actually very high, generally like 0.9 around, and then you interchange the material of the two strings with each other, okay, so that they combine together to form new strings. So, you are exploring new regions of the solution space. And what you do in uniform crossover, you are taking, for example, the first element here and first element here, and you have to decide whether to keep it as it is or exchange them. So, how do you do that? You'd say toss a coin, and if you are getting heads, you are going to keep it as it is. If you are getting tails, you are going to interchange. So, in other words, you have 0.5 probability that you are going to interchange them, and you do the same thing for every element, every position here. You either change it or you don't change it. Okay. So, this is what is called the uniform crossover. And then you have the endpoint crossover. So, here 3-point crossover is used. So, at random you choose 3 crossover points. So, the first part you are not going to cross over. Then after the first crossover point, from the first crossover to the second crossover point, you interchange these. Then you come to the third part, and here you don't interchange them. Then you come to the last part and you interchange them. Okay. So, this is what is called the endpoint crossover. So, we can see there are a number of ways in which you can interchange or use crossover basically. And what is mutation? Mutation, according to probability of mutation, you change the bit from 0 to 1 or from 1 to 0. So, for example, if you have chosen this bit and you say you are going to mutate this bit, if it is 1, you make that bit 0, and if it is 0, you make that bit 1. Okay, so these are the 3 basic operators. There are other smaller operators which are also used. So, we will just talk about these 3 basic operators. So, these 3 basic operators are used over here. Then we come to the fitness. The fitness is a measure of the goodness of the algorithm. It's a probability whether the organism will live for another cycle or not. Okay. Okay, so probabilistically better solutions have a better chance of conferring the building blocks to the next generation, because first you are going to carry out selection, which is based on the fitness, and only then you are going to do crossover where the building blocks are interchanged between strings. Okay. And so, when you get a new population, the new population is again evaluated, and you see what is the fitness of the new population. Okay, so here we will see one example. So, it is the same example I spoke of, where you are taking 0 to 31 and you are maximizing x squared. So, we represent it by a binary code, and we have a population size of 4. 1 point crossover we are using, bitwise mutation, roulette wheel selection. Okay. Actually, deterministic selection is easier, random initialization. So, let us see what we are doing here. So, suppose this is your initial population which you get randomly. So, each bit over here is generated at random. Okay. So, you either generate 0 or 1 at random and you get the random population. So, this gives you the x value and this is the fitness value. So, once you get the fitness value, we have the total here, and this gives you the average. So, if you take the total divide by 4, you are going to get the average, and 576 is your maximum over here, right. So, if we take these values and divide it by the total, we get these probabilities. So, the probability for string 1 is 0.14, 0.49, etc. So, if we multiply this by 4, we are going to get the expected count. Okay. So, since we have 4 strings in the population, if we multiply it by 4. So here suppose we are using deterministic selection, we are going to choose one copy of the second string because the integer value is 1. So we get one copy and one copy of the fourth string. Okay. Then we look at the fractional paths. So in the fractional paths 0.97 is the highest. So we get one more copy of this second string and the next highest is 0.58. So we put one copy of this. So what you get is one copy of this, two copies of this. This one is weeded out and you get one copy of this basically. Okay. So what we get is this new population here. So we have put one copy of the first string, two copies of the second string and one copy of the fourth string. So suppose next we need to do crossover. So crossover point is chosen at random. So let's say we have chosen these as the crossover point here and this is the crossover point. You are going to get these strings. Okay, so these two are interchanged basically and here these three are interchanged with these three. So if we look at the x value here, okay, so this is 12, this one is 25, etc. If we take the fitness and we get the total fitness, the average fitness, maximum fitness. If we look at the previous values here, you find that there is a improvement in this. So once you have done the crossover, you do the mutation. So this is the strings we have after crossover and you have decided to mutate two strings here. So this 0 has become a 1 and here this 0 has become a 1. So this is your population which goes into the next generation and this gives you your fitness values and this is the total fitness, the average fitness and the maximum fitness and you find that this is much better than in the previous generation. So previous generation we had a total of 1170 and 293 was the average, whereas here we have 2354 and 588 is the average and maximum also has improved. So this is how the genetic algorithm works. So this is just a very simple example to show you how this works. Okay. So let us look at other representations than the binary. One more representation you can have is that instead of using only zeros and ones, you can use integers. Okay, so it's something like using gray coding. So instead of 0 and 1, you have other integers also are possible and you can use same crossover mutation there also. And you can also use floating point variables. Okay, even floating point variables are possible and you can use crossover mutation and that also. So all these things are definitely possible in the representation. There are also other kinds of representation which is used. For example, if you want to do traveling salesman problem, you use one type of representation because what happens is it tells you the cities, city 1, city 2, city 3, say you have 10 cities. No city can be repeated again. Okay, it's just the tour of all the cities that you have. So in this way, the representation can be changed depending on the problem that you are trying to solve. Okay, and you can use different population models. So what we saw till now is the simple GA, which uses a generational model. It means that every string is there only for one generation. Okay, and the entire generation is replaced by the next generation. At the other end of the scale, you have what is called the steady state GA, SSGA. So what do you do in SSGA? Only one string or two strings are changed. The rest of the strings remain the same. Or you can have in between what is called the generation gap. Okay. So one generation gap of 1 means you are replacing the proportion of the population that is replaced. So if it's 1, you are replacing the entire population, or you could have some fraction which will tell you how many are being replaced in the next generation. Another important concept used is what is called elitism. So suppose you use elitism, it means that in every population, when you move to the next population, there will be one copy of the best string in the previous population. So that is what is called elitism. So all these things help you to come up with better solutions. It's also possible that if you have some knowledge of the problem at hand, instead of setting the initial population at random, you can set it by knowing that information. So you can start with better strings, making it easier to get more exact solution. So this will give you what GA is about in a very brief way. And we can see all the domains where applications are available, right? Control, design, scheduling, robotics, signal processing, game playing, etc. So let us look at the machine learning aspect here. Designing neural networks, which I spoke of, improving your classification algorithms, classifier systems. For all these things, you can use genetic algorithms basically. So you take almost any domain you want, you can use genetic algorithms over there to get good results in some applications. Okay, so we'll go to other algorithms which work in the same way. The next one is what is called the Tabu search. So in the Tabu search, we use only one current string at a time, and taking that current string, we find say a number of neighbors of that string, and after finding a number of neighbors, you take the best neighbor and you move from this current string to that string and call that as your current string. But what you do here is you have a set of positions which are known as the Tabu list. So every point where you have visited in the near past, they will be there in your Tabu list. So you don't move, they are actually forbidden moves, okay, unless you have what is called the aspiration criteria, which overrides this Tabu restriction. Okay, so what you do is you start with the current configuration, evaluate the criterion function and generate a set of candidate moves, okay, and evaluate their criteria function. If the best is not Tabu, or if it is Tabu but satisfies the aspiration criteria, you move to that current position, okay. So in other words, you pick the best move which is not Tabu, and then you repeat this procedure for a fixed number of iterations and pick the best configuration you have found so far. And every configuration which is chosen to be the current configuration is put onto the Tabu list. So suppose you have X elements in your Tabu list. If all of them are full, what you do is you put this new current solution into the Tabu list and remove the solution which was put earliest in the Tabu list. So that's how you update your Tabu list. And if the move which is Tabu, okay, is better than the best known so far, okay, then the aspiration criteria is met. So even though it is Tabu, you still choose it as your next generation. So this is the algorithm which is given here. Okay, it's a little confusing. So first one is the initialization step. So you have AC and JC to be the point and its evaluation, and you let AB is equal to AC and JB equals to JC. So this AB gives you the best point so far basically, okay, and then you need to choose the following parameters: Tabu list size, the probability threshold, okay, number of trial solutions, etc. So using AC, generate NTS trial solutions, okay, because NTS is what we have chosen here. And then you evaluate them and you order those, okay, once you have ordered them in ascending order. So this is the cost we are using, so we are using an ascending order. And then if the first one is not taboo, or if it is taboo, but um, satisfies the aspiration criteria, then you move to that point, okay. And if not, you go to the next one and you keep going till you find the one which is not taboo, right. Then once you have chosen one current solution, you insert AC at the bottom of the taboo list and let TLL, that is the number of elements in your taboo list, equals TLL plus 1. And if it becomes greater than the maximum, you delete the first element in the list, okay. If JB is greater than JC, then you put JB is equal to JC, because JB gives you your best up to this point in time, okay. And if K is equal to IT max, if you have done for enough number of iterations, you come out, you stop, and your JB, what you have stored in JB, okay, and your AB is your point and JB is the evaluation of that point, that gives you your final solution. So this is the taboo algorithm, the taboo search, yeah. One more search that we will see is the simulated annealing. So simulated annealing, again you are going from one current point to another current point. So what you do is from the, so this is inspired from the annealing in metallurgy. Slow cooling of the material is done and it's equivalent to slow decrease in the probability of accepting worse solution. So what you do is you suppose you find the difference between the new point and the present point, okay, and the new point is better than the present point, than the current solution, you move to that. But if it isn't, then you calculate this probability here, okay, which is e to the power of minus delta E, which is the difference between the two, divided by t, okay. Now this t, actually you are starting with a high t, and as you go on in the algorithm you keep reducing this t. When you reduce this t, this probability keeps coming down, and then when this probability comes very low, okay, that means t also is becoming very low, very small, some value say below 0 or point something, you stop at that point, and the best solution which has been selected so far, that is the one you are going to choose. So you are starting with high t. For example, you may start with a t of say 10 or something, and every time you reduce it by the cooling rate. So suppose your cooling rate is like 0.9, okay. So 10 into 0.9 will be 9. So the next value of t will be 9, etc. Or you can use 9.99 or something. So what you find is that your next point will be 9.9 or something, 9.8, etc. And you keep going down till your t becomes small. So here is the algorithm over here. So what you are doing is, S is your initial solution, S star is your best solution so far. So number of iterations is 0, T is equal to T naught. So that is the temperature you are starting at. So while T is greater than your final temperature, which is some small value, okay. So in this inside one, you are going to pick a neighbor and you find the difference between them. If this is less than 0, then you take the new one and accept it as your present solution. But if it is greater than 0, it means that the new solution is not as good as the old solution. So you find this probability, and depending on the probability, you are going to find a random value between 0 and 1, okay. and if x is less than this probability which you have got, then you accept it, otherwise you don't. So basically what you are doing is, even if it is worse, you are going to accept it, and the reason you are going to do this is to avoid the local minimum or the local maximum problem which we spoke of in the local search algorithms, right? And once you have done this a few times, once you have done it say iter times, number of, say maybe like 10 times or whatever you have put iter as number of iterations, then what you do is that you reduce your t, okay, then again you continue the whole thing and you keep on doing this till your t is falls below your TF, and then you come out of this algorithm, and when you come out of this algorithm, the best solution that you have generated so far, that is the one that you are going to return. So here we can see that we are not using any population, we are just using one current solution and we are finding one neighbor at a time, okay. So the what you would need to store here is much less. So in the case of Tabu search, we had to store like number of neighbors, and in the case of genetic algorithm, we had to store a population of solutions. But in the case of simulated annealing, it's much faster and you don't have to store much. The storage that you are using is much less because you are only storing the current solution and finding the neighboring solution, and either moving to the neighboring solution or not moving to the neighboring solution. So that is the simulated annealing. So these are three methods of stochastic search which I have told you today. So for now we will stop here for the search algorithms. Later on I will talk something about swarm and swarm intelligence for carrying out search. But as of now we are stopping the search algorithm. So problem solving agents which we started are going to be stopped at this point in time. Except for the genetic programming, which I will talk about in the next session.